Swayam Prabha. Digital India. Educated India.
Okay, very good morning. We will start the course, and I hope you had a brief introduction about this high entropy alloys from Gerhard Wilde. Of course, I know that currently he is teaching the diffusion aspects, right? So, what I am going to start is like introduction to microstructures and crystallography of compositionally complex alloys or high entropy alloys, and we will look at some basic aspects of phases, morphology, type of grain boundaries, and second phases. So mostly I will look at the phase selection rules, and what governs this phase evolution, and what decides what type of phases will be stable. Basically a thermodynamics and little bit of a geometric effect I will just touch upon. It will overlap with what some of the contents of what Gerhard will teach, but that is good because you should know how it interconnects the ideas. And the morphology and types of grain boundaries mostly come in microstructures. So mostly I will not be able to cover in this class, but it will come in the future classes. Probably I will also combine with that characterization because I can show what kind of morphology and grain boundaries can form. Okay. So look at this image. It's colorful, and this is my first slide to give you an idea about what kind of crystal structure we talk about. So this is a schematic crystal structure with the 10 kinds of atoms. You can see it is different type of atoms are connected at different lattice points. But if you have a close look at this, each one is having a different diameter, and then you have interstitial space also quite randomly distributed. And but still you can call this as a crystal structure because it is occupying some kind of a ordered lattice. You have all the atoms occupying an ordered lattice. On the other hand, it is very interesting image. This is from this book. Most of the ideas I am taking from this book by Professor A and his colleagues. And what you see in this image is a simulated amorphous structures. It represents simulated amorphous structures, 8 kind of coins. So what is the difference between these two images? Okay, ordered or disordered, you can say that. So one is, you can always call it as an amorphous structure. This is an ordered crystal structure. Okay. So in a metallurgical term, we call this as a solid solution forming a crystal with the 10 types of dissolved atoms. Why we say dissolved atoms? So different atoms occupy the same lattice. Though the atoms are different, but they occupy the lattice positions of the parent or matrix, whichever we define. Always we call matrix as the components which is more, right? That is a conventional metallurgical terminology. But here we say it is dissolved atoms and a solid solution forming an amorphous structure simulated by 8 types of coins with a large size differences. Okay. So thermodynamically, what is the point we are trying to understand is the high entropy mixing could enhance the formation of solid solution. This is a very basic physical metallurgy idea, and from there we will take it up. What is that relevant to high entropy alloys? So this is just a And this diagram is slightly different from what I have shown in the previous slide. And what is interesting in this slide is, can you just tell me the difference between what you have seen in the previous slide and this slide? That is one thing, lattice is distorted, very good. And any other observation, I can compare this with the previous one? Okay, very good. So, you have some lattice, but it is slightly distorted, but it is not randomized. But you have not having a same atoms here, you have different elements. Okay, this is important, right? So, this is called a random solid solution structure. Okay, when you do not have a same element occupying the lattice position, it is called a random solid solution structure, but ordered. It is not, amorphous. Okay, it is not disordered. Long range order, what I mean, when I say order, that conveys a different meaning in a metallurgy, right? What we talk about is a long range order as compared to amorphous structures, right? So you have the random solid solution structure unique to high entropy alloys, composed of arbitrary elements A, B, C, D and E, organized in a distorted face centered cubic crystal structure. So, this is in a FCC lattice. Instead of having a single atom, you have about 5 different atoms or elements occupying the FCC lattice position, but it is distorted. Okay, so this is another. So, what we are trying to get is a similar kind of idea or thought of designing this high entropy alloys. When you have different elements, at least 4 or 5 equiatomic elements, when we can put together, then that can form this kind of a lattice structure. That is our thought process. We will come to that science bit closely. So, some compositions achieve a single crystalline structure where each constituent element has an equal probability of populating a given lattice site. Okay. So, you have a choice how you mix, how many elements you mix, and then you have to find a probability of each elements to occupying the lattice sites. So, we do not know, because it is only a probability how it is going to occupy the each lattice site, and that is why it creates a randomness. So, this randomness creates this random solid solution schematically, where A through E occupy a face centered cubic atomic lattice structure. The uncommon observation from these reports sparked the interest of material science community. So, when you have these kind of lattice structure forms, for a conventional metallurgist it is quite different. It is very different from when I look at the iron lattice or copper lattice or nickel lattice. When I look at this kind of a random solution, but disordered crystal structure, it is quite interesting for material science community. And people just started looking at some of the basics. And what you are now looking at here is a very interesting diagram from this paper by Eso George. And what you have to focus is, I have 3 elements. One is green, red and blue. 3 elements I am trying to mix. And what are the possibilities? What do we know so far from metallurgical knowledge? This is what summarized in this figure. So, some of the possible reactions that can occur when 3 different elements represented by these colors of spheres are mixed in equal proportion. This is important. They are mixed in equal proportion. Okay. And then you observe very different kind of concepts, spinodal decomposition. So, these 2 are spinodal composition, where you have a fluctuation in the composition. Then you would have heard from Gerhard yesterday, he was explaining this, right? What is this kind of, he was explaining this, right? Uphill diffusion kind of thing. So you have a possibility of getting this spinodal decomposition, or you can have a single perfect solid solution. You can have this. The corresponding free energy concentration curve is shown here. Or you can have a situation where intermetallic and solid solution forms. This is also a possibility. Or you have multiple solid solution forms. Okay, this is also a possibility. So this is a well-known idea in metallurgy, right? When you mix three elements of equal proportion, these are all the possibilities already. Okay. But what this A and co-workers proposed is something very different, right? They provided an additional intriguing rationale for investigating these alloys. They hypothesized that the presence of multiple 5 or more, this is important, 5 or more elements in a near equiatomic proportions would increase the configurational entropy of mixing by an amount sufficient to overcome the enthalpies of compound formation, thereby deterring the formation of potentially harmful intermetallics. So the idea is very clear. You can mix any number of elements together, but the question is whether it forms a solid solution and remain as a solid solution. It should not decompose to any other compounds or intermetallics. Then there is a question, and that is where the thermodynamic basis is given here. So you make the configurational entropy of mixing by an amount sufficient to overcome the enthalpies of compound formation. So then this kind of a structure can prevail. So in addition to all these possibilities of getting this phase transformation, what I have just shown here, and this is a kind of a new idea. Okay, this is not going to happen, but then you are going to have something very different. So if you look at the literature, how the phases are defined for this high entropy alloys, they are often classified as random solid solution like FCC, BCC, ordered solid solution, for example B2L12, and intermetallic phases, for example Lavis phases. And there again you have further classification of this intermetallic phases like ordered solid solutions. They have a composition ranges which are typically ordered. So we can look at the classification of the phases in high entropy alloys according to their structure. Either it could be a simple or a complex or ordering. Okay. A structure can be simple or complex or ordered or disordered. So under these terminologies, we can classify these phases of high entropy alloys. That is one preliminary idea. All these terminologies are not new. The question here is, we are not going to have a unary or binary. We are going to have a multiple component or multiple principal elements alloy. They have different names given in the literature, but we will see how to understand all of them. A phase is simple if its structure is identical to or derived from FCC, BCC or HCP structures. So you are familiar with this notations, I hope. Suppose if I read that Cl2W, Cf4, these are all space groups, right? So crystallographic notation for each structures. And then ordered version is R superlattices such as Cp2 for cesium chloride, which is a B2 structure, and Cp4 for gold, AuCu3, gold copper alloy, which is an L12 structure. That is, one is the previous B2 is a BCC lattice and L12 is an FCC lattice. So you have sublattices. And if it is not coming into this above classification, then it is not called simple. For example, Lave's phases, it is said to be complex. Therefore, the above three types now become simple disordered phase, simple ordered phase, complex ordered phase. So these three are the primary classification for high entropy alloys, which is widely accepted in the community. What you have to remember is the high entropy alloy research is only 12 years old according to this reviews, whatever I am reading and the books. So the concepts people reported, they are all creating scientific curiosity, but some of the concepts are being proved or accepted experimentally, some of them are questioned. So the new ideas, whatever we discuss, so you should take it as a kind of an idea, then you have to see how you can experimentally prove that, right? So ideas are new and different scientific groups are examining those, and some are agreeing, some are not agreeing. So you don't have to believe whatever you see, but you can just take it as a new idea which you can also think during your research. So now we slowly go to that phase selection rules, how the phases are going to form. Having looked at some of the basic definitions like what kind of, how do we classify phases, now we move on to phase selection rule. What is that you are seeing here? You are seeing a plot of delta H mix versus delta. So what you know, this basic equation, delta G mix is equal to delta H mix minus D delta S mix, okay, and the small delta is nothing but atomic size difference, okay. So the atomic size difference is given by square root of sigma I to the power n, I from I equal to 1 to n into xi into 1 minus di divided by sigma j equal to 1 to n xj dj whole square. So x is composition of ith element and xj is the composition of jth element, and di is the diameter of ith element and dj is jth element. So this is an atomic size difference is defined like this. There are different other ways are reported in the literature, how you can differentiate this parameter, but this particular book take this as a parameter to differentiate. So what you are seeing here, delta H mix versus delta plot, and then you have very interesting region marked like S, capital S and capital S prime and B1, B2 and then C. So what is that we are learning from here? If you look at this, the filled squares which represent the solid solution forms only in the region marked S. So what does that belong to? It belongs to very, very low delta value, that is atomic difference values are pretty small, and then you have reasonable delta H mix value. It is not, it is pretty high because it is not low enough to form any intermetallic compound. So it only forms a solid solution, right? So most of the solid solution forms with the high delta H mix with a small delta value. So that is the first point. And if you look at the area enclosed by S prime clearly shows both solid solution as well as ordered solid solution. which is open circle. I hope you are able to see that in the screen. So you have, what is the difference? So you have a slightly higher atomic size difference here, okay, which is clearly demarcated from the solid solution boundaries. But here you have both ordered solid solution as well as a solid solution, a disordered solid solution. You can say that, okay. But if you look at the higher atomic differences, delta, higher delta, and you see that the B1, which is a region pertaining to bulk metallic glasses, okay. You can also see that high negative delta H, okay, as compared to this. And you also have some regions B2 also pertaining to bulk metallic glasses. So the kind of, I mean, you can define some kind of a rule based on this. I have to have so much of enthalpy range with a delta value. So for solid solution formation, ordered solid solution formation, intermetallic formation, you can define a range of values. So that is why this is called the phase selection rule. And this plot is slightly different from the previous one. What is the difference? Yeah, it is 3-dimensional plot, but what is the additional parameter? Okay, okay, delta S mix is also plotted. Why it is plotted? Because why delta S is taken? Yeah, delta G is equal to delta H minus T delta S. Suppose if the delta S component goes up, what happens? So it becomes higher temperature, it means more stable, right? Single solid solutions become stable. So to bring that also into this idea, how things are looking at. You can look at, this is very interesting now. For a solid solution where you had the delta H value, delta S mix is also very high, right? So delta S mix is also high. So the reason why we are looking at is, you look at this, all configuration entropies mentioned here are calculated for high entropy alloys, assuming that they are in the liquid or fully random solid solution state. So that is why you need that parameter to look at delta S mix. Then how the delta S mix is for solid solution is quite different from the other ordered solution. You can see that intermediate phases has lower delta S mix and also high negative delta H mix. They are all here. And then you have very high delta atomic size difference and very low delta S mix for bulk metallic glasses, and also very high negative delta H mix. So it gives a kind of an idea, okay, what are the thermodynamic parameter I have to look at it to realize our formation of these phases. This is another representation of the same idea, but what is given here is a new parameter omega, okay. So this is another parameter by which these phase forming or phase selection rules are looked at, and here also you can see that the solid solutions, intermetallics, or solid solution plus intermetallics and bulk metallic glasses, they a kind of having a distribution here. So look at this area which is marked by this color. It's a kind of a rule, okay. You should have 1.1 of omega and about 6.6 delta is required for fully forming solid solutions, okay. To form a perfect solid solution, when you mix multiple alloying elements. So you can have some kind of a cutoff. Your, delta is about 6.6 here and omega is 1.1. So this is what defined here, right? That is defined here, Tm into delta S. This is another parameter by which small delta is atomic size difference. Omega is, it is defined like this, Tm into delta S max divided by delta H max. This is a kind of normalizing with enthalpy. So you have kind of a rule to arrive at a solid solutions when you mix multiple alloying elements. So this gives kind of a guideline. So that is quite fine. And the same thing you can look at the other form. This instead of delta, you just replace delta with the number of elements you are mixing. Then you get a very different idea, right? Where you have as the number of elements increases, you can see that solid solution formation of omega also increases, right? So you can see that, and then you have a very small n values and omega values for bulk metallic glasses. And of course, you have a mixed solid solution and intermetallics comes in this overlapping region. So these are all some of the phase selection rules for producing high entropy alloys, and this is considered to be a geometrical effect. And how about the alloys which is containing other than transition elements? Like most of the high entropy alloys discussed in the literature is all transition elements, right? So now suppose if you are having elements like aluminum, magnesium, lithium, zinc, copper and so on. So this phase selection rule do not hold, they just break away from there. So you need a different ideas for this. So what you are seeing here is you can see that various parameters what we have already used. One is delta H mix versus delta, and this is delta chi, this is electronegativity versus delta. This is a valence electron concentration versus delta, and this is omega versus delta. So this, when you have these kind of a light elements, the configurational entropy does not seem to be dominant factor controlling the phase selection in the low density multi-component alloys containing significant amount of them. So this is what I was just mentioning. Some of the general rule do not apply to most of the new ideas, like for example low density multi-component alloys, and you need a special or different rule. So you can have the different threshold values for a given parametric criteria. And what is the, for example, if you have a solid solution to form at a smaller value of delta, which is less than 4.5%, and larger value of delta H mix, which is minus 1 kilojoule per mole, and it should be in between 5 kilojoule to 1 kilojoule, minus 1 kilojoule per mole to minus, minus 1 kilojoule per mole to 5 kilojoule per mole, and larger omega. So this is a kind of criteria for elements involving low density, which is quite different from the high entropy alloys which is forming at forming with transition elements. Okay. So this is one idea. What you can see in this image very clearly, the hatched area representing the previous phase formation rules, whatever we have just seen, but the data points clearly shows that they are all slightly deviating from the the phase formation rule with the transition metals. In fact, if you look at this VEC versus delta, all the data points go outside this hatched area. So that is why it is quite. So which one to follow when you have different type of alloying elements? That is something we have to look at a new methodology of selection rather than the conventional idea. So that is the message. So I will slowly now move to some of the basics of physical metallurgy idea of high entropy alloys. I hope that Gerhard had told you already about this, some core effects of these materials, something called core effects, right? One is high entropy effect, another is he has told, right? High entropy effect, sluggish diffusion, lattice distortion, cocktail effect, and so on. Again, all these effects you have to keep it with question mark. Okay, these are all initial ideas people have observed and people suspected, and then they have given some justification, but not all the systems are obeying this, but some scientists are reporting different ideas. But if you look at the a bird's eye view picture, you take a given composition and then you process and then produce a particular microstructure with aiming or targeting a particular physical and mechanical properties, and how these effects are coming into play, these core effects, so-called core effects. So high entropy effect is from thermodynamics, right? Because a normal solid solution forming rule we all know, that is Hume-Rothery rules, right? Hume-Rothery rules. So in addition to Hume-Rothery rules, we are having some additional thermodynamic conditions in the case of high entropy alloys. And so when you talk about kinetics of phase transformation, this sluggish diffusion comes into effect. And of course, the deformation theory, they will all connect to this severe lattice distortion effect. This is not new to us because we have been talking about solid solution strengthening where we talk about lattice distortion, or we can deform the material by cold rolling or hot rolling. There also we are getting a distorted lattice. So, and then we know the benefit of all these kind of ideas already. You know what we do, what we get out of cold rolling, what we get out of severe alloying. Superalloys are there for last 40-50 years. Everybody knows, hardness goes up, and when you increase the cold rolling reduction, again strength goes up, work hardening comes into play. All these things are known, okay. But what is when you have a multiple principal elements in the matrix and how these effects are looked at? That is the difference, right? All these ideas are known, but how when it comes to high entropy alloys, they are addressed. That is the idea. So I will just show some examples which is given in this research paper. It's quite interesting that it is a demonstration of high entropy effect. For example, you have X-ray diffraction plot for a copper nickel, and then you slowly add elements aluminum, and then aluminum cobalt chromium, aluminum cobalt chromium iron, aluminum cobalt chromium iron silicon. So what is that you are seeing from copper nickel to the alloy which is formed? What is the difference you are seeing from in terms of okay. Okay. So you start with one crystal system, then it becomes quite random. You have mixed of FCC plus ordered BCC. Then again this ordered BCC disappears to disordered BCC. So the number of phases, I mean, coming down as you go, it all converges into kind of a two-phase mixture or a single phase in some cases. So, the high entropy effect states that the higher mixing entropy, mainly configurational in HEA, lowers the free energy of solid solution phases and facilitates their formation, particularly at high temperatures. Right. So, due to this enhanced mutual solubility among constant elements, the number of phases present in high entropy alloys can be evidently reduced. So, this is the idea. So, the idea of high entropy effect is this: the number of phases present in the alloy can be evidently reduced, even though you keep adding several elements of this size. So, this is a kind of an example how you can visualize high entropy effect. And this one is a very nice illustration again, showing that what is a distorted lattice and its various interaction with dislocation, electron, phonons and X-ray beam. So, when you have this kind of a scenario in a normal lattice, what will happen? Suppose if I replace this lattice with a normal lattice, a uniform, undistorted, still a dislocation can go through, still a phonon can go through, then you have an X-ray can go through, an electron can go through. What difference it will make? Suppose if you imagine that I do not have this a distorted one. In a normal lattice, what do you expect in terms of these dislocation, how the dislocation will pass through, or how electron will pass through, or how phonon will pass through that lattice, and how X-ray will pass through the lattice? What is the difference if I replace this? Or you just tell me in a normal lattice, what do you expect? Then we will come to this. Then it is easy to compare. Suppose if you come to this random, this kind of a distorted lattice, it is not only distorted, it is just each atom is surrounded by a different environment. So, the bonding is different because of the one atom is bigger, another atom is small, and then you have a vacancy, and then that bonding is different, and again the atoms are different. So, what will happen to this the dislocation, suppose if it wants to pass through? Will it be easy or difficult, or X-ray will easily go through, or that is the question.
There can be some
In every case, there is a difference. There is some difference because of the field it generates around each atom is quite not similar. So, you are going to get a very diffuse scattering because you are not going through a normal lattice, because each atom diffuses, scatters in a different magnitude. So, that we will see it when you come to the characterization. In a normal lattice, how you look at the microstructure or a diffraction pattern, and this kind of situation, how it changes, that we will see. Even a dislocation as such, it will go through if there is a no problem, a proper lattice, you need a force, but then here you need a much higher force because of more complexity. So, this is the idea, phenomenon, you have to keep this in mind. Every atom in multi-principal element matrix is surrounded by different kinds of atom and suffers a lattice strain and stress, both. Okay. So, in addition to atomic size difference, different bonding energies. Yeah. Why I am saying bonding energy? Because one atom is bigger and one atom is small. So, that the connecting bonds to the neighboring atoms will not have the same energy. So, that is the idea. And the crystal structure tendencies among the constituent elements are expected to cause even higher lattice distortion, since the non-symmetrical neighboring atoms, non-symmetrical binding and electronic structure around an atom, and the variation of such a non-symmetry from a site to site would affect the atomic position. So, your interatomic position, if you just think of this kind of a lattice, how complicated it is. You cannot just give an average value of in a normal circumstances. Here it is, every interatomic position is different. So, that creates a quite a bit of a strain, distortion. So, this is a simple idea, schematic, nice schematic to think about, and continuation of that process. Now, we are looking at little more nice comparison. What is the difference between left and right? Left is called the dilute solution model, and right hand side is a complex concentrated solution. So, what is dilute solution here? Why do we call it dilute solution? No, why are we calling it as a dilute solution? Some solutes are there, but that fraction is too small. That's why it's called dilute solution. And but dilute solution, you have, even though you have a different atoms, but their fraction is too small. On the right hand side, you have the complex concentrated solution, where there is no dominant atom species or atom positions usually deviate from the mean lattice positions. Suppose if you try to calculate the mean, atomic, I would say interatomic distance for a given direction, it is too complex. So, and then you have to take all the average from all the directions. The variability in the atom positions in structure B, that is complex concentrated solution, contributes to an excess configurational entropy. So, what is excess? So, that is clearly visualized here. Okay, when you say excess entropy, we write in thermodynamics, right? What is excess here? The excess is coming from each lattice positions. The variability of each lattice position contributes the excess configuration entropy. So, that is one thing. So, let us look at some of the core ideas, points from this previous slide. The degree of lattice distortion is one of the 4 proposed high entropy alloy core effects. I would say this is the most important effect of high entropy alloy, which is supported by almost everybody, and everybody looks at the effect of this. There is no contradiction. It influences solid solution hardening models, and it contributes to excess configurational entropy, and it is implicated in the difficulty in distinguishing between ordered and disordered phases via X-ray standard diffraction techniques. This is what I asked in the previous slide. From these kind of a lattice, XRD interpretation is not going to be easy. Whether it is coming from ordered or disordered, how to distinguish that peak from this kind of a environment is a challenge, because it is going to alter the peak positions. Crystal lattices in multi-principal equiatomic alloy phases are almost certainly distorted, but there are no systematic study to explore and quantify this feature directly. How do we study this? It's a huge challenge, right? How do you study? What are the techniques you can think of? We are going to do characterization in the coming classes. What technique you can suggest for such a? People are saying there is no systematic studies to explore this. So, the commonly used delta R, that is a change in atomic size diameter, quantifies the variability in atom sizes, but distortion in the structure can be less. So, there are people doing like what you said, doing a transmission electron microscopy. Lattice fringes are traced on inverse fast Fourier transform images. And this kind of gives some idea about the distortion, how the FFT, inverse fast Fourier transform, taken from the high resolution TEM gives some kind of idea. So, this is again an open question, how do we do this and how to quantify this, what is the magnitude of lattice distortion. It's a still evolving technique. A lot of people have created methodology based on the peak shifting, like what you see in a diffraction, electron diffraction also. They have written several codes, they are available now, but they are all from very local regions. Okay, so what is this? This is another example to showcase this so-called cocktail effect. What is cocktail effect? Did Gerhard talk about it? This is another terminology given in these textbooks, cocktail effect. You have very different property. It is not the summation of the properties of the elements given there. Because of the interaction, something new is added, that is being described as a cocktail effect. And what is shown here is the hardness versus aluminum content. You can see that a series of alloy are designated by the sequential addition of one extra element to the previous one. Then you can see that one or two major phases that have a simple structure like FCC, FCC plus BCC and BCC, they are formed. This is partly because of the formation of a hard BCC phase. Why the hardness increases? Because of the FCC to BCC transition is a hard phase, and it is partly due to the stronger cohesive bonding between aluminum and other elements, and it is larger atomic size. So, this is also a factor. So, you have how to summarize the cocktail effect. The macroscopic properties of high entropy alloy not only come from the average properties of the component elements, but also include the effects from the excess quantities produced by the inter-elemental reactions and lattice distortion. So, this is important. So, that is considered as a cocktail effect. It is not just a summation of average properties of the components which are already there. It is an excess quantities produced from the other interactions. So, we have looked at three major core effects introduction, but sluggish diffusion I am not getting into, Gerhard will do it, and these are all familiar to you already. So, I just want to emphasize and recast the idea. So, now we will slowly go to, yeah. Strain, lattice strain, yes. Because you are adding aluminum, which is, you are adding aluminum to a matrix which is smaller than the aluminum size, atomic size. So, then it is producing a lattice strain, and then so now we will go to another interesting question. What is the question here? What kind of phase or crystal structure will form when we mix so many different elements together? How do we know? We are going to just mix randomly, and what kind of phase and what kind of phase, already we have some idea. Phase selection rules, we have talked about it. What about crystal structure? So, that is the question. What kind of crystal structure will form when we mix so many different elements together? And we have given some kind of introduction to this phase. What kind of phase? Simple structures, that is simple disordered phase, simple ordered phase, okay, are most frequently seen in the as-cast high entropy alloys. Okay. You can have a BCC, FCC, they are all simple disordered phase, or you can have L12, B2, simple ordered phases. So, these simple phases originate from high entropy effect mentioned previously. Besides simple phases, different kinds of complex ordered phase also will form, such as sigma, mu, Laves. They are also observed in high entropy alloys. Because simple solution phases with more than 5 elements are unique to high entropy alloys, so the researchers have worked intensely to understand the condition for their formation. So one thing is at least clear, when you say high entropy alloys, you should have minimum 5 equiatomic elements, and then you start looking at how it forms. So the question is, suppose if I mix 5 equiatomic elements, so what kind of crystal structure will form? Is there a rule, or is there a idea? Do you have an idea? Suppose if I mix 5 equiatomic element, equal proportion, what crystal structure I should get? Is there any idea? Hume Rodri gives something, but that is only for binary. How do we think about it? How do we understand that? Anyway, this is a similar plot what we have already seen. This is of course thermodynamic effect. I am just reinforcing that idea, because people have just given some kind of threshold values for the ordered and disordered cases. So the similar plot we have already seen in the previous slides, but what I am trying to show here again, to form sole simple cases or simple phases like FCC or BCC and their mixtures, including both ordered and disordered cases, the following conditions have to be met simultaneously. That means their enthalpy of mixing should be between -22 to 7 kilojoule per mole, and delta should be less than or equal to 8.5, and entropy of mixing should be between 11 to 19.5 joule per kilo per mole. So this is a kind of experimental window people have already reported. If you want to form a simple phases, but it is again they are predicting only a mixtures. It could be FCC, or it could be BCC, or it could be a mixture of everything. But at least you have some conditions available. What kind of crystal structure will form? Is it possible to control the formation of FCC or BCC structured solid solution high entropy alloys? That's a very interesting question, right? So you look at this plot. Again, delta H mix and atomic size difference. So if you have an FCC type solid solution forming, delta range largely overlaps with the BCC solid solutions. In the middle, you have both FCC, the red ones are FCC and BCC, the black ones are FCC alone, and of course the blue ones are intermetallics and green ones are BCC. So they are overlapping here. Dependence of crystal structures on the enthalpy of mixing and the atomic size mismatch for various high entropy alloys. So this gives some kind of thermodynamic drive, what kind of crystal structure you will land up. But most important parameter is this, electron concentration. Okay, electron concentration has been known to play a crucial role in controlling the phase stability and even the physical properties of alloys. So in a Hume Rodri compounds, or so-called electron compounds, also talks about this valence electron concentration or E/A ratio. Okay, that is also there. And in the literature, they discuss both E/A ratio as well as valence electron concentration. But for high entropy alloys, only valence electron concentration gives a great idea what kind of crystal structure it will form. This is what people have reported. Okay. So, this plot what you see here is you have just as a function of valence electron concentration, you have a pure BCC and FCC BCC mixture and pure FCC. You can see that the relationship between VEC and the phase stability, you can see that. So, valence electron, what is valence electron concentration, by the way? You have any idea? Okay. Is that alone? Your answer is correct, partly, but high entropy alloy literature says something differently. They say that since it is done for mostly transition metals, they also include the d electrons, number of d electrons plus the electrons in the valence shell. That is considered valence electron concentration. Yeah, so d electrons plus valence electrons, valence shell electrons. So, what is the, I mean, is there a rationale? Firstly and qualitatively, yeah, in a solid solution forming high entropy alloys, BCC phases are stabilized at lower VEC, while the FCC phases are stabilized at higher VEC. In intermediate VEC, both FCC and BCC are formed. This is what I showed in the previous plot, and there are some numbers given for an FCC phases to occur, or VEC should be greater than or equal to 8. For BCC phase to occur, it should be less than 6.87. And for a mixture of FCC and BCC phases, it should be in between 6.87 to 8. So, this is a kind of a guideline by which you will be able to predict what kind of crystal structure it will form. So, therefore, the VEC rule provides a convenient way to design FCC or BCC structured high entropy alloys containing mainly transition metal elements. This is an important point. And from the electron concentration perspective, and its validity has been verified widely by the subsequent experiments. So, this is already experimentally verified by different researchers. So, can we use this for something else? Valence electron concentration. Some researchers have used this quantity to predict the formation of sigma phase in cast alloys. Okay. So, they have identified the values for VEC in the range of formation of sigma phase 6.88 and between 7.84. Why this is sigma phase formation is important? What is sigma phase? I said it is a complex, it comes under a complex ordered disordered category, and you have the window where a VEC from 6.88 to 7.84, you will form a sigma phase, and if you avoid these numbers, then it is sigma phase free. Either it is less than 6.88 or it is beyond 7.84. So, valence electron concentration forms a basis for predicting the crystal structure formation in high entropy alloys, as well as it gives some idea about how to prevent the sigma phase formation again. Microstructures, yeah, we will finish in half an hour. So, what kind of microstructures we are looking at in high entropy alloys? A wide range of microstructures have been produced in complex concentrated alloys, including amorphous, nanocrystalline and single phase, multi-phase conditions. This particular review what I have given here by miracle. They have studied, they have collected information from 408 unique alloys, and some alloys are evaluated in more than one paper and more than one process condition, giving a total of 648 unique microstructure reports so far. This gives some kind of a statistics. What are the possibilities? We are talking about multiple alloys, and everybody is today working on this high entropy alloys. So far it is 648 unique microstructure. When you say unique microstructure, what do you mean? Grains and grain boundaries and different phases. Could be a single phase, two phase. It can have defects, or it can have a second phase. All of them. So when you say unique microstructure, that means each microstructure will have a very specific fraction, phases, defects, second phases, and so on. And then out of this, 23 different crystalline phases are found. Crystalline phases itself 23. So how do you imagine 23 phases? What are these 23 phases? I will start with FCC, BCC, HCP. Then I can mix with A1, B2, L1, 2, all intermetallics, or I would say intermetallic compounds or intermetallic solid solution, ordered intermetallic, disordered intermetallic. Everything is considered a individual crystal structure. So when it get mixed with the basic things, you will produce so many. So if you are interested, you go through this references. They have given all the tables. It's a very nice review for high entropy alloys. Yeah. So out of 648 microstructure reports so far, what are the statistics at least? The number of times each phase found in this all microstructures is, first you see that FCC, mostly it is FCC, then comes to BCC. Your HCP is too small, very, very small. Though we talk about HCP, and the people look at that number is too small. Okay. And then you have B2, sigma, C14, L12, C15, E9, nickel titanate, DO2, L21, all this. And some phases are fewer than 4 times, not shown in this. So that means you have additional crystal structures like A5, A9, A12, C16, DO22. All this interesting, crystal structures. And of course, some of the phases also have amorphous phases which are not counted here. So all of these are either intermetallic compounds or ordered or disordered intermetallic compounds. And the important information you get is FCC is the predominant microstructure so far in high entropy alloys, followed by BCC. Then how do they classify in terms of solid solution or intermetallic plus solid solution? How do they classify? This is a very interesting plot. For example, you have solid solution. Solid solution has single phase, 2 phase, 3 phase. There again, so you have about nearly 50% of solid solution you get. Out of that, you have 3 variations. Again, intermetallic, you have single phase, 2 phase, 3 phase. And solid solution and intermetallic mixture, you have again a variety of phases. You have 2 phase, 3 phase, 4 phase, 5 phase, 6 phases. So this is more complicated microstructure. And then what do you see here? In single phase, what is the fraction of this solid solution and intermetallic? If it is single phase, you have primarily solid solution, small fraction of intermetallic. If it is a two phase, then you have individual phases and then mixture, and three phase, the total percentage is coming down. As the number of phases increases, the percentage of occurrence is decreasing. So this is an idea. If you have a 6 phase, then you look at the fraction is pretty small in terms of mixture, composition. So this gives some idea about what are the different microstructure can form, and that can be related to our previous idea, what we have just looked at, the thermodynamic idea. And what I have shown here is people looked at this phase formation prediction. They use a lot of empirical correlations to separate solid solution, intermetallic, and a mixture and amorphous and so on. What are these empirical correlations? Empirical correlations, even Hume Rothery also gave empirical correlations, and people added to this. People added thermodynamic parameters. Theoretically, they calculated, and then they compared with how much is true, because you have n number of possibilities of mixing, and then you do not know how do I select the phase selection, how do I define the phase selection if I keep on adding elements. Then I need some modeling helps little bit to reduce the experiments. So in this case, this empirical calculation also helps in reducing that selecting the right combination of alloying elements and how many phases it will form, what crystal structure it will form. So for that, people have done this. So you can see that the correlation is done. Both correlation separate solid solution and amorphous. But in the case of intermetallics and solid solution intermetallic mixture overlap these two regions. So again, this is and what you see in B is an ASCAS data are typically used to support these correlations. What is predicted in the left hand side, it is almost these plots already you have seen. I have shown that in the earlier slides, and it you can see that overlapping area of the mixture. And the practical implication is annealing reduces the extent of the solid solution region. So that is what is shown in A. Okay. So it's an anneal, you can show that the solid solution region shrinks. So that is one idea. Another important point is most of these alloys, compositionally complex alloys or high entropy alloys, they are studied in the as-cast and annealed conditions, and in that conditions what are the how the distribution happens. For example, if you have if you take a solid solution, after annealing it reduces, it has some effect on the volume fraction. As-cast has significant effect in an intermetallic, and in a mixture it is an opposite effect. You see that as-cast and annealed has a different occurrence percentage, and then similarly you can relate that with the single phase, two phase and three phase. So this is some idea about what kind of crystal structure we are dealing with. Here again a comparison of the observed experimental measurements as well as the CalFAT calculations are estimated by structure in, structure out analysis. This structure in, structure out analysis is nicely given in this paper, where they have set some kind of parameters based upon the CalFAT calculation and other calculations, whether your experimentally observed structure falls within that or not. So that is the structure in, structure out calculations. Based on that, they have segregated this, and then the observed content is the number of times a phase, whether it is a BCC, FCC or HCP or the microstructure, is normalized by the total number of observations. And this structure in structure out analysis is based on the crystal structure of the constituent elements at melting point, or in the percentage of binary systems in a collection of alloys that are ideal or regular solutions. What you see here is, you see that the red ones are CalFAD and the blue ones and violet ones are experiments. So you can see that there is a kind of agreement between these two. This is my last slide, and we will stop here. And what it summarizes is that what we have looked at experimentally, what kind of microstructure it will form and what CalFAD predicts, they are all shown here. So what is that summary, what we are trying to get? These comparisons are all show the related trends. Compared to the calculated CalFAD results, experimentally observed microstructures favor solid solution over solid solution plus intermetallic mixture. Okay. And favor few phases over more phases, and favor FCC phases over BCC or HCP. So this is an idea. FCC is considered to be highly favorable phases formation in the microstructure. And measured microstructures give a strong non-random sampling of preferred elements and grouping of elements, while CalFAD, the calculations represent a more uniform exploration of elements. So what it tells is, like, you have the experimentally observed solid solution and intermetallic phases, and they are more or less agree with what CalFAD predicts. So this gives some kind of introduction to what type of microstructures you get in a high entropy alloys. And what I will do is, in the next class, I will show the actual experimental results, some of them, and then I will take it forward to the how to characterize this complex microstructure.